Okay, I'm going to do this by kind of waving my hands instead of writing anything on the board because it would involve doing a three-dimensional sketch. And if you're not used to looking at three-dimensional sketches, it wouldn't be very helpful. But if we have X, Y, and Z, I can do this much. I can say we could represent a graph of X, Y, and Z in three dimensions. Okay? It's like your Y-axis is here, your X-axis is here, or X-axis is this way, Y-axis is here, Z-axis is up here. Okay? So kind of like, anyhow. Okay? Now, without going any further on this, I can simply say that every one of these equations, the X's, Y's, and Z's that satisfy this equation, for example, form a plane, like a sheet of glass, oriented somehow in three-dimensional space. We can even say that, okay, if Y and Z are both 0, X equals 6. Well, that means that sheet of glass has to go through the point, let's say that's where X equals 6 is. 6, 0, 0. 6 for X, 0 for Y, 0 for Z. If X and Z are both 0, Y is 4, so we would have a point maybe here. And you don't totally need to understand this, but if X and Y are both 0, Z is equal to -3, so we would have a point down here. So we could kind of do a little triangle with these points and get an idea that this plane is cutting in this direction. Now, whether you totally understand that or not, the analogy is if you have just this equation, and this is an X and this is a Y, let's say, okay? An equation in two variables, that just gives you a line, right? So if it's just an X and a Y, an equation, if we get off the Z, you get a line, okay? And that would actually be this line in the three dimensions, but that's not what's important. What's important is that this equation would also give you a plane. Okay, the plane might be oriented differently. Now, if you take one plane and another plane, where they meet is a straight line. Okay? So that this plane and this plane meet on a straight line. That straight line is in both planes. It's the straight line where the two planes meet. Okay? This plane is parallel to this plane. Okay? And it's parallel because, well, how do two lines end up being parallel if their slopes are the same? Right? Okay? Can't make a perfect analogy to that, but I mean I could, but it wouldn't be a good idea. Okay, this plane is identical to this plane because if I divide through here by 2, I get this. This equation, I cheated, I just doubled this equation. Okay? So the solutions to this equation are identical to the solutions to this equation, meaning that these two planes are the same. That means that this plane is a little bit different. It's parallel to this plane, but it never meets it. Just like two lines are parallel, these two planes are parallel, but they don't meet. These two planes are parallel, but they do meet. They're identical. Just as in a system of two equations and two unknowns, if your lines turn out to be the same, then you have infinitely many solutions on that line. Okay? These two planes turned out to be the same, so we have infinitely many solutions. Pick any Z, You can find a y and then an x that satisfies all of them. Okay? But this plane never meets this plane because they're parallel. So you have that analogy. So you might see that. It's kind of a neat thing to think about, but it's a little bit challenging. The one thing to take away from this is each of these equations is a plane. It's possible for two planes to be parallel but never meet. If they never meet, there's no x, y, and z that lies on all the planes. So there's no solution. The planes don't intersect, you don't have a solution. Okay? Usually, if you just make up numbers, the three planes will never intersect. I mean, three planes will never be parallel. Very seldom will they be parallel. And you'll have a solution. Because if you have three planes, take two of them. If they're not parallel, they meet on a line. And then if that third plane is not parallel to one of the first two, it'll intersect that line and you'll have a point. Okay.